In this video, I want to talk about the performance of merge sort. So let's take a look with respect to an algorithm we've already talked about, which is insertion sort. So insertion sort is O of n squared. Merge sort is O of n log n. Okay, so this is the performance, right? We'll have to do some analysis later to get to it, but just let's try to appreciate how nice it is to have an n log n algorithm. So looking at insertion sort, I have this little table here. My table has a couple different axes here. Right, first is basically input problem size. So I could have 1,000 elements, 1,000,000 elements, 1,000,000,000 elements. I have that kind of my problem sizes, and then I have a choice of computers. I could run this on a supercomputer or a home computer. My two choices. Okay, my tables here are showing me approximately an amount of time it would take to run this algorithm on this type of computer, given the size of input. Okay, so we have this table here, right? Maybe ask yourself the following, right? You can hopefully pause the video and think about it. What helps out more in terms of performance? Having a faster algorithm or a faster computer? So think about that. Okay, so hopefully you thought about it a little bit. It's going to be the faster algorithm. Okay, so I just look at my chart here. Here, right, I have like basically what I want to do is I want to look at the largest one. The largest one to me is going to be kind of the worst case. I look over for insertion, so right, home computer is 317 years, supercomputer is 1 week. That's a lot of time. But then I look over at merge sort, 17 minutes. Okay, 17 minutes versus 317 years. That's a huge factor, right? That's a lot. Over here, right, instant versus 1 week, same factor again, right? And so here, right, even though this is a nice speed up, 1 week, so it's like, well, so 317 times 52, right, is the speed up here, but instant versus 1 week, right? That's many more times than that. So yeah, in general, right, we always want to go for that faster algorithm, right? Even though we could just throw more hardware at something and we would get a faster result, it'll be a result that's well, it's faster, but it'll be faster by maybe by like a polynomial amount of time. It won't be that much faster, okay? And also it's hard. So hardware also, right? There's other problems with it, right? Things like cost. I have to buy the thing, I have to power the thing. It's another resource to manage, right? The algorithm, right, is basically sort of like instant speed up, right? It's like you've defined your problem from the very beginning to be faster, right? And that's generally going to be a better approach. Typically, right, we do have this huge speed up, right, that occurs. If you go and look, you can see there's charts of these things. That'll basically show you, performance over time, and it's like n squared, right? As input increases, it looks something like that, versus log n will look something like that, right? And it's just because it's n squared versus n log n, right? Think about it in terms of the big O analysis. That n log n is going to win. Okay, so having a faster algorithm like merge sort is clearly going to help us out. All right, so here I kind of started with the claim that merge sort was n log n. We haven't really talked about it though. For the other sort of algorithms that we did, we spent a lot of time talking about properties, and we tried to elucidate, how many comparisons they needed, how many exchanges they needed. We did all of that work. We found the following results. Right? We found, selection sort looks like this, insertion sort looks like this, shell sort we're not quite sure. It's somewhere between there, but more research is needed. We do the same thing for merge sort. Now the issue here though is that when we did that analysis for selection sort and insertion sort, those were iterative algorithms. They weren't so bad to analyze. It was just a bunch of loops that we could look through and kind of figure out how are things how are things falling. Maybe we could draw a picture, try to figure out what's going on. Not too bad. Shell sort of course was more tricky because we had the whole gap sequence, right? And that was basically defining effectively it's defining, right, a sequence, a family of different sorting algorithms, right? And those are kind of hard to characterize, hard to understand. Merge sort. Well, merge sort isn't that bad, but the problem is it uses recursion. Because it uses recursion, we need to do something about that recurrence. So what we want to eventually do is basically write a big O analysis for this, right? That'll have a growth function that is recursive and try to find a non-recursive version of that growth function, okay? And that'll be a little bit of work. We did do one example, right? We're doing that with the towers of Hanoi. The one for merge sort, though, will be significantly more complicated because it's not going to be as straightforward as, just doubling each time. Because this time we're going the other direction, we're splitting down. So we'll be doing that in a couple of videos. We'll basically have that full discussion of taking this algorithm, doing that analysis, and figuring out for sure that it's O of n log n time.